The environments these agents train in are hand-built by human engineers. Once they are built, they remain completely static. Because they are static, these worlds are entirely blind to an agent's specific weaknesses. If a model struggles with a particular type of logic sequence, the environment cannot adapt to test or teach that exact skill. As the agent's policy improves through training, the original environment rapidly loses its utility. The model masters the fixed tasks, and the static world is left behind. The traditional fix for this problem is having a large language model generate entirely new environments from scratch. That approach carries a massive engineering burden, and worse, introduces a critical flaw. The agent ends up being graded by unreliable, self-written verifiers. Maintaining the original, trusted human grader, while a wrapper endlessly remakes the tasks, shifts the priority of agent development. The primary asset becomes the harness that instruments the environment. That is the premise of EnvHarness, a programmable layer of plugin components developed by researchers at Google Cloud AI. This layer wraps around a static environment to reshape its behavior, modifying tasks and layouts without ever touching the underlying logic of the world itself. This chart shows how the system is decoupled. To run this layer, the system uses a companion agent called EnvRigger. EnvRigger treats the target policy as a black box. Observing trajectories, it diagnoses systemic failure patterns, like submitting patches without running tests. EnvRigger synthesizes new harness components, targeting these weaknesses, validating them on fresh rollouts before deploying into the loop. We recently covered a system called SPADE that attempted to solve the static environment problem. The caveat with SPADE is that it writes both its training worlds and the checks that score them, which inevitably inflates the reported gains. EnvHarness is a direct answer to that vulnerability. Because the wrapper only alters the task presentation, the original, human-built verifier is entirely preserved and isolated from the generative process. Decoupling task generation from task checking gives the agent a denser optimization signal to learn from, while entirely avoiding the inflated grades of self-scoring synthetic worlds. For researchers evaluating this system, the true utility is found in the second-order capabilities, rather than the top-line performance numbers. Specifically, this architecture introduces difficulty as a dial, a primitive control mechanism that has been missing from curriculum learning. This dial shows the system's ability to normalize success rates. The project documentation demonstrates the harness taking tasks with an 80% success rate and tasks with a 6% success rate, and steering both directly into a requested difficulty band of 0.4 to 0.6. Having a precise dial for task difficulty enables true, sustained coevolution between the training policy and its environment. The researchers ran 3 rounds of this coevolution on SWE-bench verified. Over those 3 rounds, the agent score moved from 47.7 to 54.8. That progression proves the environment can actually keep pace with the policy's growing capabilities, rather than being immediately exhausted and left behind. They also tested reinforcement learning on EnvHarness environments against reinforcement learning run on the original unmodified AlfWorld tasks. The agent trained in EnvHarness achieved an 88.3% success rate, compared to 85.4% for the original environments. This gap indicates that the reshaped worlds carry a much denser optimization signal for the agent to learn from, rather than simply offering a higher volume of tasks. These outcomes suggest that generating new tasks and new checkers simultaneously is not a requirement for creating denser training signals. For builders engineering agent systems today, this architecture is highly deployable right now, largely because the underlying code is public. It also carries a distinct architectural advantage. The wrapper strictly preserves the standard reset and step interfaces that developers already use to manage agent environments. Furthermore, because EnvRigger only needs to observe execution trajectories to diagnose flaws, it is fully compatible with closed-weight, API-only models. The paper provides a clear benchmark progression using Claude Sonnet 4.6 on SWE-bench verified to demonstrate this exact use case. As a base model, Claude scored 67.2. When allowed to learn in real environments, that pushed to 69.2. But when training inside EnvHarness environments, the score reached 72.4. Tracking deployable, API-compatible breakthroughs exactly like this is the specific focus of this channel. If you want to keep pace with these shifts in production architecture, subscribe below. However, implementing this system introduces some severe unknowns, starting with the actual compute cost. The entire diagnose, synthesize, validate loop that powers EnvRigger burns extra model rollouts purely to set up the environment. This is an upfront cost entirely separate from the compute required for the actual training runs. The paper completely omits a compute figure, a rollout budget, or even the number of validation runs required per generated component. If you plan to deploy this, you have to budget for those hidden costs before accepting the paper's framing around computational efficiency. Beyond the unstated financial costs, there are serious security implications regarding what breaks when this is deployed in a production setting. The core risk is that these harness components are entirely model-written code executing directly inside your evaluation loop. While a pre-commit hook that enforces test runs is benign, unleashing an automated agent to author components against your integration pipeline creates a massive injection surface. The paper treats this automated authoring as a capability feature, but if you deploy it, you have to own it as a critical security risk. Those risks frame the context for the paper's primary headline claim, that EnvHarness delivers a 9.0-point improvement with 9.8% fewer execution steps. This table shows 3 setups. The 9.0-point gain compares against the untrained base agent, an unfair baseline. To find the true value, compare the models that actually trained. Against the original benchmark agent, gains shrink. WebArena is 3.1, SWE-bench 2.7, and AlfWorld 5.9. The math is straightforward. The actual value added by dynamically reshaping the environment over simply training inside it is roughly 3 to 6 points, not 9. A consistent 3 to 6 point gain across multiple domains is highly scientifically valuable, but the up to 9.0 headline flatters the system by leaning on a comparison to a model that never left the starting line. We also need to scrutinize exactly what the paper means by held-out instances in its abstract. In this specific context, held-out instances means test cases from the exact same benchmarks that EnvRigger initially used to diagnose the policy's failures. Because of this setup, the evaluation is only measuring how well a highly tailored curriculum generalizes to sibling tasks within a tightly scoped known domain. Nothing reported in the paper tests cross-benchmark transfer. There is currently no proof that the agent learned generalizable skills that would carry over to an entirely new, unseen environment. Without evidence of cross-benchmark transfer or a transparent rollout budget, this system functions as highly effective benchmark tailoring supported by a respectable grader.